Okay, we're now going to talk about solar photovoltaics, which is the fastest growing form of renewable energy and the one that's probably going to do most of the work to decarbonize the world. Now, here's a reminder of the powers involved. This is a slide you've seen before. Full direct sunlight has a power of about 1000 watts per square meter. That's facing directly towards the sun on a clear sunny day. If you factor in things like nighttime, clouds, the sun being low in the sky, the average is more like 200 watts, depending on location. Even on a heavily overcast day, maybe 25% of the sunlight is still getting through. And whenever sunlight actually lands on a solar photovoltaic cell, a PV cell, typically about 20-25% of that will be converted to electrical power. So let's go through how these things work, and these slides are mostly borrowed from Kylie Catchpole. So, just to give a sense of the scale, this map shows the average solar radiation in kilowatt hours per metre squared per day across Australia. And you can see that there are good regions and there are cloudy regions. But that little red circle here would supply all of Australia's electricity if it was covered with solar photovoltaics. And the big green circle would supply all of the world's electricity if it was covered in solar photovoltaics. So there's just an awful lot of power in the sunlight falling on the Earth. It's the biggest source of energy supplied to the Earth, and you don't need to cover the entire Earth with solar cells to do anything. A very, very small fraction of the Earth will power all the electricity we need. Now, the most commonly seen solar photovoltaic systems are on the roofs of houses. So a typical solar cell on a roof would produce between 2,000 and 9,000 kilowatt hours per year, which is enough to offset all the electricity use for an efficient house. This is a 1.3 kilowatt system. This is a much bigger 5.5 kilowatt system. My house, it happens, has a 1.6 kilowatt system on the roof. Now, the solar cells produced direct current electricity, DC, which is not what actually drives most appliances and to the grid. So that's fed to an inverter, which is typically a box on the side wall, which converts it from DC into AC, alternating current. And then some of that could be fed indoors to power your house. And if you've got more being produced than you need, some of it is fed possibly into a battery, but also can be fed back into the grid. So that's a smaller scale. On larger scales, you can get commercial buildings like this, which is the Crown Plaza Hotel in Alice Springs, which is a 305 kilowatt solar system on the roof, which produces 530,000 kilowatt hours per year, which is 420 tons per year of carbon dioxide avoided. And then you get the big commercial plants. Now, these are cheaper in terms of electricity per dollar, because everything is mass-produced rather than being carefully, you put it on flat ground rather than having to climb on the roof and worry about brackets and everything else like that. So these are the most efficient, cheapest things, these big commercial things. This is Greenup River Solar Farm in Western Australia, 10 megawatts, provides enough electricity for 3,000 households. And there are bigger ones, much bigger ones. This is a Darlington Point. So it's a 275 megawatts photovoltaic farm, 27 times bigger, near Griffith in southwest New South Wales. And around the world there are much bigger ones than this as well. Now, the photovoltaic these photovoltaic cells are produced at the rate of typically 1 cell per second in huge factories. A typical new factory will produce 1 gigawatts worth of solar cells, about 600,000 modules per year. Most of these are in China, and they're huge, heavily automated, extremely efficient factories that produce huge numbers of these things, which can then be shipped around the world and put on people's roofs. How much of this would you need to power the world? Well, the world electricity consumption averages about 3 terawatts. That's 3 by 10 to the 12 watts of power on average, day and night. So as we've just said, one huge factory can produce about 1 gigawatt of panels per year, So over a 20-year period, it'll produce 20 gigawatts of power. So to get 3 terawatts, we need about 150 giant solar panel factories, which is not ridiculous for the entire world. That's one per country, if you spread it uniformly around the world. And you need to cover about 600 square kilometres with solar panels every year. That sounds enormous, but it's a 25 by 25 kilometres square, and if you do it somewhere sunny, and there's plenty of desert and sunny areas in the world, so again, it's not totally ridiculous. What is a bit scary are the mineral needs. So to produce enough solar cells to generate 1 megawatt of power, you need 2.5 tons of polysilicon. And as the amount of solar cells produced gets larger, that means a lot of polysilicon is going to be produced. Now, the raw material silicon is common and cheap, so it's not too hard. But like in 2011, the world is producing 280,000 tons of polysilicon. That's now up to about 600,000 tons. And in 8 years' time, it'll be probably 4 million tons will be needed. So we need a drastic ramp up in the number of factories producing the polysilicon that can be turned into these cells. 4 countries between them control 98% of the polysilicon market. That's China, Germany, US, and Malaysia. We also need silver, but to lay the cables in the front to get the electricity out, and of course copper wiring to connect the whole thing. So we're going to need massive increases in silicon and copper mining to support the huge increase in photovoltaics we're going to need.